There we go. That's nice. All right, here we go. Number 31, chapter 17. All right, so on the recording, chapter 17, number 31. This one should be just kind of plug and chug, hopefully, right? The formula on the formula sheet is given as Q equals CV. We're asked for capacitance, so C equals charge per volt. And then we're just plugging in, then, you know, it's just kind of plug and chug. 2,500 microcoulombs in 850 volts gives us 2.9 times 10 to the negative 6 coulombs per volt, or farads. Yes, do we all agree?
Yes.
Excellent. That's what I thought, right? So that one should be simple, was real simple, just kind of plug and chug. Next one is number 34. I'm going to stop, pause the recording. All right, this time we're doing number 34 in chapter 17. And again, hopefully it was just plug and chug. Into the formula, we're solving for the charge that flows from terminal at a 12 volt battery and it's connected to a 7 microfarad capacitor. So again, in the formula sheet, it's given as Q equals CV. So we're just substituting in. The capacitance was, what did we say it was? 7 microfarads times 10 to the negative 6 farads and a 12 volt battery. So we're just multiplying the two. 7 times 12 is 84. So 84 microcoulombs. Is that right? Yes. Good. Simple enough, I think.
Yep.
All right. Next one is, again, not very complicated. It goes up this much more level in difficulty, but should be a gimme. Number 6, or number 36. All right, I'm going to pause the recording again. Quick. All right, this time chapter 17, number 36. Again, the level of difficulty going up just the smallest amount. This time we are told the charge on the capacitor increases by 18 microcoulombs when the voltage increases from 97 to 121 volts. What's the capacitance of the capacitor? So again, Q equals CV. This time we're asked to solve for C. So C equals volts per, do I have that backwards? Yes, I'm doing it backwards. Q charge per volt, right? The charge we're given as 18 microcoulombs, 10 to negative 6 coulombs. The voltage, I keep trying to find a dark marker. I don't know if it's dark enough on the screen. The voltage changes from 97 to 121, so it's 24 volt increase. And when I pushed the buttons on my calculator, I got 7.5 times 10 to the negative 7th farads is the unit of capacitance. All right. Do we agree?
Yep.
Yes, we agree. Okay. I wanted to talk about what the idea of, real quick, use this to build on just the idea of what a capacitor is again. The idea is of a capacitor is the device, this physical device. The capacitor is a physical device. So the capacitance of a capacitor doesn't depend on the charge, it doesn't depend on the battery that it's hooked up to. It doesn't depend on anything. The capacitance, its ability to store charge only depends on the design of the device. Okay, but once you hook it onto a battery, onto a voltage supply, depending on the amount of voltage that is hooked into it, the amount of charge can vary, as long as that ratio stays the same, right? So the idea here is, so essentially like the battery on your phone is, and rechargeable batteries are effectively like, they're very similar to capacitors in the fact that they store charge, right? And as you plug it in to recharge it, more charge is added into this capacitor and stores it. So, right, our symbol again looks like this, or parallel plates. Sometimes it looks like this. And then in a circuit, the symbol of a battery looks like that. So the charge leaves the battery. This is the battery. The charge leaves the battery, gets to the capacitor and starts to gather on the plates of the capacitor. This would be the positive side because that's the positive side of the battery. This would be the negative side. That would be the negative side of the battery. So you'd have a positive charges collecting on this plate and negative charges collecting on the other plate, right? If you think about if you ever, like, I don't know if you've ever paid attention to the time it takes to charge your battery of your cell phone. If your cell phone's really kind of empty, you know, you're down to 10% and you plug it in. Initially, the percentage of charge on your cell phone increases fairly quickly at the beginning. And then as you get closer and close to that 100% charge on your cell phone battery, it takes more and more time to increase a smaller and smaller percentage, right? Have we all noticed that at some point in our lives? Or is it just me being a physics nerd? Am I talking to anybody?
I got you. Yeah.
Okay.
I don't think I'm.
All right. So the reason that happens is as the capacitor gets more and more charge on it, it can only hold so much charge depending on the battery or the how much voltage, how much potential energy is coming out of the battery or the plug in the wall. So as it fills up, it gets harder and harder and harder to put those next charges on the plate. So it takes more and more time to finish off the charge of the battery, right? When the battery in your phone is empty, it's easy to put more charges on it. But as it fills up, it's harder to cram the last charges in. So that's why it starts off increasing quickly. And as you get to the end, the rate it increases slows down. All right, so can we kind of visualize what's going on there? Right? I just wanted to kind of give us a more visual understanding of what we're talking about. And then it just can store that energy in there. Good? All right, let's move on to the next one. I'm going to pause the recording and we'll move on to the next one. Now, the next one. Okay, number 37, we're told we have an electric field of 8.5 times 10 to the 5th volts per meter between two parallel plates, where we're given the area is 35 centimeters squared and the distance between the plates is 2.45 millimeters, excuse me, and we're asked for the charge. So in order to find charge on a plate, right, number 37, charge is equal to capacitance times voltage. So we need to find the capacitance and find the voltage, right? Voltage is the electric field times the distance, right? Right. Volts per meter times meter going to give us volts. So the voltage is, I work this out here, 8.5 times 10 to the 5th volts per meter times the distance between the plates, right, is we're using the distance between the plates, 2.45 times 10 to the negative 3rd meters, right? 2.45 millimeters. -3 and +5 is 2. So 8.5 times 10 squared is 850. 850 times 2.45 is 2082 volts. The capacitor is made as an air gap, so it's K E sub O A over D. And for air, the constant is 1. So the E sub O constant is 8.85 times 10 to the negative 12. I forget what the units are, to be honest. Something like farads per meter. I don't remember. I'll look it up. Area is 35 centimeters squared. We need to convert our centimeter squared into meters squared, so all our units match. All right, so if you didn't do that, then that might be an issue. So 3.5 times 10 to the negative 3 meters squared, right? Not 35 centimeters squared, but we need to convert it to meters squared. And the distance between them, again, 2.45 millimeters is 2.45 times 10 to the negative 3rd meters. My 10 to the negative 3rds cancel. 8.85 times 10 to the negative 12 times 3.5 divided by 2.45 gives us, I got 26.2 times 10 to the negative 9 farads. Oh, that's wrong.
Yeah, Mr. Shuka, do you need the constant for the dielectric for air?
Yeah, the dielectric constant for air is like 1.000059.
So just round to 1. Okay.
I just made it 1, right? I copied the wrong number here. The capacitance is 12.6 times 10 to the negative 12 farads. And then I can substitute, right? 12.6 times 10 to the negative 12 times 2082. I got 26.2 times 10 to the negative 9th coulombs of charge on that capacitor. Good? We all good with this? We all understand how to make that conversion, right? All our units have to match. All right, I didn't bother going through the process of the conversion, but we have to convert to meters. Everything has to be in meters. We good? Anyone have any questions? I went through it kind of fast. All right, I'm going to take your silence as you are good. So I'm going to pause.